So the other terminal value for d equals for p equals d by 2 is that is in that case you have logarithmically divergent diagrams. So therefore, this analysis tells us that curly P, which is the set of primitively divergent diagrams, corresponds to P equals 1 to D by 2, which is of course a finite set of diagrams. So let us now take an example of D equals 4. Show that delta n greater than 0 in D equals 4 means phi cube interaction. And in the phi cube interaction, the two diagrams, so D equals 4 means the value of P will be 1 and 2. D equals 4 means D by 2 is 2. So P equals 1 and P equals 2. P equals 1 means there is one loop and one vertex. So this is phi cube interaction, and one loop and two vertex will be this one. The value of omega, let me list it here. So value of omega is fixed when you fix number of dimensions, so d, and the value of p. So p equals 1 in d equal to 4 means omega will be 2, and similarly for p equal to 2, omega will be 0. So there are two values, two graphs, omega equal to 2 and 0, irrespective of what kind of interaction we are now listing here. So for delta n equal to 0, your interaction will be phi to the power 4. In this case, the first primitively divergent diagram is one loop, one vertex, which is this one, and then one loop, two vertex, which is this. And delta n less than 0 will give you phi to the power 5. This one, and phi to the power 6, which will have one loop, one vertex. So there are two lines here, so there are 4 more lines coming out. And so on, all higher powers of phi, these are all in this group delta n less than 0. So this is the list of primitively divergent graphs for various theories, phi to the power n theories. Now let us look at E graphs. Now starting from such a graph, P graph, primitively divergent vertex, you can add more loops on them. Like for example, you form a loop like this, and try to create more divergent, more graphs which are divergent. I mean, which have omega greater than 0, greater than or equal to 0. But typically, it is possible in some cases to add a loop without adding vertex, and but if you have to add a loop like this with some other lines, then that will increase the number of vertices as well. So the way to construct find E graphs is to add up more loops on top of the existing P graphs. Typically, such a process also increases the number of vertices. So if delta n is greater than 0, then omega reduces as v increases. So such a process cannot continue forever. Therefore, such a number of such graphs cannot grow indefinitely as the spectrum of omega greater than or equal to 0 is finite, and with increasing v, graphs become more convergent. Okay, let's see, let's demonstrate this for the phi cube theory. Phi cube has delta n greater than 0 in t equals 4. So this is our primitive graph, and we add a loop on that like this. But we also add 2 vertices. We can continue doing that, another loop like this, or we can add the 3rd loop in this manner. In all these last 2 cases, v will be increased by 2. So let us now calculate the value of omega in each such cases, in each of these cases. So this is a 2-loop diagram. 2-loop means there's 8 powers of momentum upstairs in 4 dimension, and the number of propagators is 1, 2, 3, and 4. So 4 times 2 minus 2 times 4, and that's 0. In this case, it is 3 loops, so 12 upstairs, and the number of propagators 1, 2, 3, 4, 5, 6, and 7. So that's 14. So this is minus 2. Here also it is the same counting, because the difference between these last 2 diagrams is that the loop is, instead of being here, it is here, but it increases the number of propagators, etc., in the same manner. So it's minus 2. If you take the other primitive graph, which is this, and add a loop on top of that, you get this. You could add the loop in this way also. So in this case, it is 2 loops, so omega will be 8 minus 2 times the number of propagators. So 1, 2, 3, 4, 5, so that is 10. That is minus 2. Similarly, here this is also 2 loop, and number of propagators is 1, 2, 3, 4, 5. So that is also minus 2. So this is the value of omega, and you can show for in d dimension d dimension the formula for omega simplifies to 4 minus, in 4 dimension, 4 minus e minus b. And you can check all this. These 3 graphs have e equals 1. So 4 minus e is 1, and then number of v. So 1 minus v. So 1, 2, 3. Sorry, 3 minus v. 1, 2, 3. That is 0. Then 1, 2, 3, 4, 5. 3 minus 5 is minus 2, and same here. Here, E equals 2. So 4 minus 2 is 2. So 2 minus V, 1, 2, 3, 4. 2 minus 4 is minus 2, and also same here. So we use the process of adding up more loops on the primitive graphs and arrived at this type of graphs, and we see that these are not cannot be included in E because they have omega less than 0. Now omega less than 0 is a omega less so omega less than 0 graphs are of two types. One is overall finite and other is absolutely finite. We can check that also for these 4 graphs. Which one is overall finite and which one is absolutely finite. Overall finite means although omega is negative, there is a hidden divergence because of a primitive graph or a non-primitive graph sitting inside as a subgraph. So let us look at this diagram. You see, there are 3 loops. The loop that has minimum number of legs, minimum number of propagators, is maximum chance of being divergent, being a subgraph for which omega is greater than 0. And that's this last loop. It is one loop but with 2 propagators. So that is one loop means 4 minus 2 propagators is also 2 times 2, 4. So this is logarithmically divergent piece. So this is sitting inside, and it is of the primitive type. It is this graph, because this can be viewed as this. So this is this second one. So this primitive graph is sitting as a subgraph here, and because of which you have a divergent piece. So although omega is negative, you have a primitive graph sitting inside as a subgraph, and the graph is divergent, logarithmically divergent. See, this graph is logarithmically divergent. None of the subgraphs in this graph is actually of the primitive type, and you see there is no loop with only 2 propagators. So this is the loop with 2 propagators, and therefore it gives you a logarithmic divergence. Here there's 1 loop and 3 propagators. Here also in this loop there are even more propagators, and so on. So these are absolutely finite. Graphs. So this is overall finite. This is absolutely finite. This is also overall finite because this one is a primitive graph, 1 loop with 2 propagators. This is absolutely finite again. Now let's look at delta n is equal to 0 case. Now in this case, omega does not depend on V, and therefore free to add more loops and hence vertices without changing the value of omega. So I made a mistake earlier. I had written it finite, it should be infinite. So spectrum of E is finite only in delta less than 0, but in these last 2 cases E is infinite. Okay, so that is what we are seeing now here. Delta n, for delta n it equal to 0, omega does not depend on V, therefore free to add more loops. Therefore, the spectrum, there is no limit to adding such loops, so spectrum of E is going to be infinite. So phi 4 interaction, this is true in general, but for in D equal to 4, delta n is phi 4. So phi 4 in D equals 4, we have this is a primitively divergent graph, and we are adding, we will add a loop on this. We can have a primitively divergent graph, which will with the two vertices, but then there are another legs, and these two legs form a loop. So you can write it like this, and so on. You can add more and more of them, more and more loops. It doesn't matter if you increase number of v or not. In this case, for example, 4 point. So when e equals 4. This is your primitive graph, and then you can add, this is a loop, you can add a loop like this, or you can add a loop like this. So in all these cases, these are going to be quadratically divergent, and these are going to be logarithmically divergent. This line omega equals 4 minus e. This formula for omega simplifies to 4 minus e. You can check, for example, here how it is 2. It's 2 loops. So 2 loops means 8 power of momentum is 8 upstairs, and then 1, 2, 3. So minus 6, that is 2. So that is how it happens. And you see, in these cases, you have there's a subgraph which is of p type. The p graph is sitting as a subgraph. So this one is a subgraph that is sitting. So this one is a subgraph, primitive subgraph. Similarly, here, this one is a primitive subgraph. This one is a primitive subgraph, and this one is a primitive subgraph. So primitive subgraphs are appearing within the graph, and that's why these are non-primitive graphs with omega greater than or equal to 0. And so that's but there is an infinite number of such graphs, and therefore the set of the spectrum of E is infinite. For delta n less than 0, the spectrum of omega is greater than or equal to 0, and therefore infinite. I mean, spectrum of omega greater than or equal to 0 is infinite, and therefore E is also infinite. There are only finite number of pre-graphs, but there are infinite number of graphs which have omega greater than or equal to 0. So the rest of them are all E graphs. You can take phi to the power 6 in D equals 4. So this is your primitive. So phi to the power 6. So there are 4 coming out, and you can form a loop like this. So that is a non-primitive. That is an E graph. Similarly, just like this one, you can draw an analogous graph here. and so on. In this case, omega is given by the formula is 4 minus E plus 2 times V. And it is 4 here, 6 here, and it will keep increasing. Okay.